Thank you very much, Fran. So just recap of where we are, what we've done last week, and these are there in the recordings and in the notes from last week. The overview of the course, how the whole thing is stitched together, and we're going to return to that material at the end of today's session to give us to talk about how you should approach the time remaining, how you can structure your work in that time, which obviously how you structure your work has to follow on from how the course itself is structured and how the exam is structured. So the key material are the mechanics, the light, sound and waves, the modern physics that we looked at on Tuesday, the electricity that we did an overview of yesterday. And today we're going to mop things up a little bit. We're going to talk about heat particle physics and revision plans and all of that combined. Before we get into that, there's a question at the end of yesterday's class about the definition of the ampere. This is a really interesting topic, actually. There are only 7 fundamental units. Everything else is based on that. So if you look at, say, something like momentum, the unit of momentum is the kilogram meter per second. It doesn't have its own unit as such. Even something like force, the unit of force is the Newton, but if you look at it, a Newton is 1 kilogram meter per second squared. So that the unit for the Newton is built on the definition for the kilogram, the meter, and the second. The kilogram, meter, and second are fundamental units. They have a much more specific definition. And there's only 7 things like that, which is electric current. So the kilogram meter per second, the amp, that's 4. The mole, 5, 6, 7. The candela, which is luminosity, how bright things are. And there's another one which is not on my mind now. But what's happened during the run of this syllabus, and it's why syllabuses have to be rewritten and rejigged every now and then, is that the definition has changed. So like there's an international body, UPAC, I think it's called, which sort of agrees all these things. And it's a combination of sort of government, bureaucracies and university departments. So the definition that we're supposed to have learned in the syllabus is the one on your screen there. The ampere is that constant current which will produce my own graphics here are blocking that, an attractive force of 2 × 10⁻⁷ newtons per meter of length between 2 straight parallel conductors of infinite length and negligible cross section placed 1 meter apart in a vacuum. So it was all a bit fanciful. So basically, if you had 2 wires side by side, 1 meter apart, and you put an electric current through both of them, well, then the 2 wires will experience a force, depending on the direction of the current, either attractive or repulsive. And they used the size of that force to define the amp. And the basic principle is fine, but it's when you get into the, well, not even small print, that it became a bit ridiculous. Because, of course, what would happen at the edge of these wires? A wire is 2 meters, as a meter apart, that's fine, but how long is the wire? And at the end of the wires, is there going to be a bigger or a smaller force? So they dealt with that by saying, oh, there is no end to these wires. They're of infinite length. And then the width of the wires makes a difference. Is it, when we say they're 1 meter apart, is that from the middle of one wire to the middle of the other? Now, it'd be a very tiny difference in any situation, but when we're trying to be absolutely purist about definitions, these things matter. So to deal with the fact, well, do we mean 1 meter from the inside of one wire to the inside of the other, from the middle of one to the middle of the other? Just to make that problem go away, they said they have negligible cross section, meaning they're infinitely thin as well as infinitely long. And then the material in between the two has an effect. Is it air? Is it water? Is it plastic? Is it oil? And to make that problem go away, they said it's in a vacuum. So straight away, the scenario used to create this definition of the ampere can never be created in reality. So it was a bit of a this definition. So May 2019, all of the fundamental definitions were rejigged, but the two that made a big difference was the kilogram and the amp. The kilogram was the most the oldest definition of the lot, in that the definition of the kilogram was it was a lump of material stored under specific temperature and pressure in a chamber in a university in Paris, and that was the size of 1 kilogram. And if that had happened to rust or whatever over the centuries, it didn't go out of, like, it was no longer slightly more than a kilogram. The size of the kilogram would have grown. It was a bit ridiculous too. And of course, how could you ever check if you were trying to say a kilogram in Ireland, is that the same as a kilogram in Paris? How do you physically make that comparison? So it was very silly. So the kilogram was changed, and I looked them all up last night, but I can't remember what it was changed to. But the ampere is this definition. It's the fixed numerical value for the elementary charge to be blah, 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 blah. So in other words, it's based now on the definition of the coulomb, and on the charge on the electron. And that's equal to the amp second. So 1 coulomb is still 1 amp second, but basically 1 amp coulomb per second rather than the other way around. The thing is, that definition, only valid since May 2019, is not listed anywhere in the syllabus. So most likely what will happen is it'll be ignored, but they did actually bring it up last year, but in this sort of way. So they had what is electric current, calculate the current flowing when electrons pass a point in 30 minutes. That's just charge divided by time. And then the previous definition of the ampere, so the one that you will have seen in your textbooks, explain why this phenomenon occurs, the 2 wires, and describe the laboratory experiment. So they brought it up, but in a roundabout way. So how do you explain how the phenomenon occurs? I've skipped. So like if you put an electric current through a wire, you're also creating a magnetic field there. So if you have 2 wires side by side, both carrying a current, then both of them are magnets, and 2 magnets side by side will always either attract or repel each other. And you can demonstrate it by hanging some aluminium foil from a retort stand, putting a current through it, and you'll see them usually jump apart. Okay, so mainly, I think in terms of the definition of the ampere, you can see that it came up last year, but in a way that avoided the whole problem about what actually is the definition now. So I would say don't be fretting too much about that sort of detail, though it's easy for me to say. If they bring it up, they will find a fair and reasonable way of doing it. Now, talking about heat and temperature and specific heats. So a basic scenario, if you put 2 containers, identical containers, on a hot plate, so they're both getting exactly the same amount of heat, so they've got the same volume, they're in identical containers, they're same mass, both with identical thermometers. After 5 minutes, will they be at the same temperature? And they won't be. Usually the oil in that scenario would heat up more quickly than the alcohol. Why is there a difference? Because of the distinction and interconnections between heat and temperature. Heat is a form of energy, which if added to a body will increase its temperature, or if taken away will decrease its temperature. What's going on at a level underneath that, and this is not like part of an official definition, temperature is a measure, not by definition, but it does correspond to the average kinetic energy of particles in an object or gas. So this is running on my screen. I hope that's getting through the broadband on your end. So if that represents a gas, the particles are moving around inside the box, that could be a room or whatever. And when that's heated up, the particles begin to rise, to move more and more quickly. The faster the particles are moving or vibrating in an object, the higher the temperature. That's not a coincidental thing. That is absolutely tied into the very meaning of temperature and heat. Heat basically corresponds to the total amount of energy. Temperature corresponds to the average kinetic energy. The definitions are more simple. Heat is just a form of energy which, if added, will increase the temperature of a body, and temperature is a measure of hotness. But those definitions, in a way, cloak the more complex reality that's going on underneath. And When you add heat, the particles will begin to vibrate or move around more quickly, but not always to the same extent if you compare one body to another. And the factors that can have an effect are the mass and the specific heat capacity, as well as, of course, with the amount of energy added. So, and the converse of this is also true, by the way, that if you take heat away, the particles will move less and less quickly until, of course, to get to the point where the particles are not moving at all. And when the particles are not moving at all, well, that's the least amount of kinetic energy you can have. So you don't, you can't go lower than that. That's why we have a lowest possible temperature. Now, how does this relate to the maths? So the energy involved in it follows this formula, mc delta theta, where m is the mass of a body, c is the specific heat capacity, and delta theta is the change in temperature, corresponding to the definition there. Now, the specific heat capacity relates to a substance like water, steel, air, whole substances have a specific heat capacity, and it is the amount of energy per kilogram. You can also have heat capacity of a body which relates to a body, a tea, like in a question we'll see, or a glass has a heat capacity, whereas glass, the material, will have a specific heat capacity. So the difference is between small c, which is the one that we nearly always use, but occasionally you'll come across this version, equals capital C delta theta. That C then relates to the energy required to heat up a whole body by 1 degree or 1 Kelvin. This simple sort of maths involved, if you have 2,100 joules, increase the temperature of a metal block by 4 Kelvin, what is the heat capacity of the block? So that's heat capacity, not specific, so it's capital C delta theta. You rearrange the formula, C is E divided by delta theta, that's 525 joules per Kelvin. But if we're asked for the specific heat capacity of the material, then that's mc delta theta with the small c, specific heat capacity, and it works out to be 656.25 joules per kilo per Kelvin. Notice the different units there. So for an object, we're dealing with heat capacity. For a substance, we're dealing with specific heat capacity. Now, as well as when you heat something up, the particles will begin to move around more quickly. That relates to temperature. There's also the fact that sometimes they will change their state. So you can have in a solid where the particles are all more or less locked into place. They're vibrating, but not moving around. If you heat it up enough, the particles will break loose and begin to glide around in between each other. That's a liquid. Eventually, if you heat it up enough, they'll begin to escape from the liquid altogether and go into the room around it. Then it's a gas. As you add energy, the temperature will rise, but it will tend to level off at a change of state. So as you have increases in temperature, that's an mc delta theta calculation, but where the graph has leveled off, you're still adding energy, but the temperature isn't going up. That's what we call a change in state. And the energy involved in change of state is the latent heat. The specific latent heat is the energy required to change the state of 1 kilogram of a substance. Now, there's a lot of background there, but mainly, know your definitions and know these two formula. The energy involved in a change of temperature is mc delta theta. The energy involved in a change of state is E equals ml. Those two formulae or terms within formulae come up over and over and over again. Let's have a look at how that might happen. It could also, and very likely would happen in the experimental section, but I've taken a question from section B here to illustrate how you can put the maths of this together. It was from 2011, and it was about hot drinks in general, but more specifically about I think they say hot drinks in general, but I have a latte in mind when I'm picturing this. So making hot drinks. Yeah,
sorry, just before you get on that, just seeing there that the polls haven't come in. If you have a chance to have a look at maybe send them on.
I will. I just have to come out of it. Stop share. I must be sending it to some other Fionn. I'm just checking my Sent. Fionn Kenna at intel.com, isn't it?
Fionn.Kenna.
Yeah. I'm just going to send them once more. And if they don't come through, then we'll just have to scratch it. So we heat up the milk to make a hot drink. Could be a hot chocolate, latte, whatever. So we add steam at 100 degrees to 160 grams of milk that's at 20 degrees, more or less room temperature. If the final temperature of the drink is to be 70 degrees, what mass of steam should be added? You may ignore energy losses to the surroundings. And a metal spoon with initial temperature of 20 degrees is then placed in the drink, causing the temperature of the hot drink to drop to 68 degrees. So what is the heat capacity of the spoon? So that's the mathematical part, which usually comes later on in the question. This is sort of upside down in terms of order and structure. Then name two processes by which the hot drink cools. This is the energy transfer. We'll come back to that. I'm using this question as a way of getting ourselves into the details. And then a little bit of a thermocouple that I want to talk to as well. So this is going to be in the polls, but we'll just run through this quickly. It wasn't maybe worth the time we were going to put into it anyway. So trying to get the idea that there are so many ordinary everyday temperatures around us that I think often don't really pay much attention to. But a refrigerator is typically kept around 4 degrees. Some should argue it should be 2 or 3. But of course, if it was 0, things would begin to freeze. It'd be more like a pretty low grade freezer. A typical freezer is at minus 18 degrees in house. The Irish Sea in July is 14 degrees. Obviously, that's an average, and it varies an awful lot from one spot to another. Even on one beach, you can get warm areas and cold areas depending on what rock is underneath the sea and when the tide came in and out. All physics, all related to MC delta theta. But the average won't vary very much from 14 degrees. It goes down to around 9 in January. Camphor, if you put wood into a fire and burn it. So that one, usually, it varies a lot depending on the wood. Heavy woods burn at a higher temperature than lighter woods. But around 900, I mean, ballpark 1,000 degrees. And then relating to this question, and really all hot drinks. So typical hot drink, what temperature do we actually like it to be at? And it's usually around 70. And when I was researching this, I discovered like a whole internet hole, as you can imagine, exists on every single topic under the sun, where people furiously argue about should it be 65 or 68 or 70 or 72 degrees. And, you know, people's whole reputations within the coffee industry are trashed on the basis of arguing for the wrong temperature. But the average, the reality, away from the purist, tends to be that most of us like our hot drinks to be pretty much 70. Anything over 80 is scaldingly hot, really way too uncomfortable, and anything down around 60 begins to feel really tepid. Some people like that, but mainly in Ireland, we like it around 70. Other countries, slightly colder. Okay, but that aside, let us look at the maths of this. So we're making a hot drink, and steam at 100 degrees is added to 160 grams of milk at 20 degrees. And you had all the information you needed at the bottom of the question relating to specific heat capacities and stuff. So if the final temperature drink is to be 70, what mass of steam should be added? So basically what we have going on here is like usually some sort of tube or metal insert going into your jug of milk. Remember, the 160 grams is going to be 0.16 kilos. We don't know how much steam, so that's our X, that's our unknown. It's going in at 100. And of course, that steam will then condense and cool down to 70 degrees because it's going to stay inside the milk, whereas the milk will have to heat up from 20 to 70. So putting the maths together with this, remember that all of these heat experiments and heat calculations all operate on the basis that the energy lost is equal to the energy gained, that we cannot easily factor in whatever energy might drift off into the room around it. So we just assume that doesn't happen. So the energy lost is lost by the steam. And then it all comes down to ML and MC delta theta. So you know that what does the steam do? It comes in here, and first of all, it changes state, so that's ml. And then that means it's turning from steam at 100, water at 100, then cool down to 70 degrees. That's a change in temperature, so it's mc delta theta. So if there's a change in temperature, it's mc delta theta. If there's a change in state, it's ml. If there's both, you add ml to mc delta theta. And what is gaining energy here is the milk. Does it change state? No, it just gets hotter, so it's just a change in temperature. And if you get that line right, you've straight away got marks for it, but you've also given yourself a structure where you can get the rest of it right as you sub in. So the X is mass of the steam, the 2.34 by 10 to the 6 is the latent heat given in question. 4.18 by 10 to the 3 is the specific heat capacity of the water. It's turned from steam at 100 degrees to water at 100 degrees. That's 4,180. By X, the mass of the steam by the change in temperature, which is 30 degrees. It has to cool down to 70. And then on the other side of the equation, how much milk do you have? 0.16 kilos. Specific heat capacity was given in the question, and the change in temperature is 50 degrees. So take those lines slow. Give yourself time to figure them out. Don't try to do it all in one go, and write down every thought you have, because that in itself could get you marks, but also it's going to help you keep your ideas clear. And then just do the algebra, multiply out your brackets, rearrange them. Don't do it too quickly. Put everything on paper, because that's where you're likely to get it right. And it comes to 0.0127 kilos, which is 12.7 grams. Right, so then a metal spoon with an initial temperature of 20 degrees is placed in the hot drink, causing the temperature of the hot drink to drop to 68. What is the heat capacity of the spoon? So there's also arguments, by the way, about putting spoons in drinks, or when you should put a spoon into drink, or after you make the coffee. So many arguments on this. But regardless, you put the spoon in, the spoon is colder, so the spoon will heat up and the drink will cool down. The hot drink, that's a change in temperature, so it's mc delta theta. And the spoon is a change in temperature. We're not asked for specific heat capacity, just heat capacity. So we don't care about the mass. This is the heat capacity of the spoon, of the object. So it's a capital C, delta theta. So put them equal, sub in, you have all the numbers. Again, we're going on the basis that the energy lost is equal to the energy gained. You sub in, C is the only thing you don't know, and it works out to 29.143 joules per Kelvin. Now, I'm not suggesting any of that is easy, but it is manageable. If there was an infinite variety of formulae, it would be much more difficult, but it all comes down to ml for change in state, mc delta theta for a change in temperature, and energy lost will be equal to energy gained. No energy disappears. So you just have to rearrange them as fits the question. Then name two processes by which the drink cools. So you only have to name two, but this is how does heat transfer. So it's convection, conduction, and radiation. Convection are convection currents. So demonstrated sometimes in junior cert, if you put a little bit of dye into water and heat up the water at just that point, you will see the dye rise. And then the heavier water at the top begins to fall down. So the actual hot particles rise, bringing the heat with them. Conduction, no particles actually move, but the vibration here, the metal particles vibrating here in a metal bar, for example, if you stick it in a Bunsen flame, that vibration moves along the wire until the whole wire, the whole metal bar is as hot, all the particles are vibrating at the same temperature. If they vibrate enough, it'll start to melt. So there, the distinction here is that in convection, the particles move, bringing the heat with them. In conduction, the particles vibrate, but they don't move from one place to another. It's the energy that moves through the material. And radiation, all hot objects emit infrared radiation and other radiations, but it's mainly infrared. And that's how heat can transfer across space. That's how we get heat from the sun, for example.
Hi, Tom.
So
just a question on the last one. It was someone wondering where you got the mass from on one of the last questions there.
the mass, oh, it was there in the very first slide, and I didn't copy it back, so I'll scoot back to it. So I mean, I'm not sure which mass, but we're looking for the mass of the steam. We're given the mass of the milk, it's 160 grams. And then when you have the hot drink, I bet you that's the one that was causing confusion. You've added, as we've calculated, the 0.0127 kilos. So that's, like I said, 12.7 grams, but in kilos, 0.0127 has been now added to the milk. So the milk is 0.16 kilos, but we've added the 0.0127 kilos of steam, which is now hot water, which is now mixed in with the milk. So the hot drink has now got a total mass of whatever that would be, 0.1727. I think that must be it. If it's a different mass in mind, let us know. So we've got the conduction, convection, radiation. And then how does each apply here? That's the bit, you should be ready with your definitions of conduction, convection, and radiation. Then how is each applied here? It's really common sense. Convection, well, how do you lose heat from convection through a coffee cup? Because the heat rises up into the air above it. Put a lid on it. Conduction, how does heat escape through conduction? Well, through the walls of the container. Which is why we often use things like polystyrene cups, insulated cups, to stop the heat escaping there. We don't lose much radiation from hot drinks. We don't lose much heat through radiation from hot drinks, but we do lose some. It would be better to use shiny metal containers, but then that doesn't work. Most shiny metal containers are good insulators, so you lose more through conduction. So it's usually conduction and convection where you lose heat more quickly. So they're the ones that we normally address. And then a thermocouple. Now, not worried too much about the question here, but how does a thermocouple work? This is something that's only mentioned in passing in the syllabus, but they do ask about it a lot. It's a simple concept, but I don't know why they're so keen on it. So you take two pieces of metal, different materials, say nichrome and copper, and you twist the edges so that nichrome and copper touch here and touch there, but not in the middle. And then if one of those junctions is cold and the other one is hot, it creates a voltage or a current. And you can measure what that voltage is and use it to tell the temperature. So particularly if you have ice and boiling water there, then you can match it all up to the Celsius scale. But the main thing is just to be aware of what it is as a device. So it's two different metals touching at the edges, not in the middle. If the two junctions are at different temperatures, a voltage is created. You can use that voltage as what we call a thermometric property, a property that allows us to measure temperature. Okay, so the marking scheme, just stressing what I've stressed all along, you get a lot of marks for any attempt. So the formula here picked you up 6 marks just for getting the formula right, 2 for each part of those. Similarly down here, getting the formula right got you another 3 marks down at the bottom. The very concept of energy lost equals energy gained got you 3 marks. So my point is, obviously some of these things get more detailed and can be tricky no matter how well prepared you are. But if it's a mathematical question, it's based on formulae. And if you write down the relevant formulae and make some attempt to sub into them and some attempt to move on from there, it's not only likely you'll have got a few marks, it's very unlikely that you won't have picked up marks, and sometimes very substantial marks, which is only fair. It's absolutely right that the people who get these questions completed get the full marks. But even if you feel you've fallen way short, if you've subbed into relevant formula and made some progress, you have done most of the work and you should get a good mark for it. The conduction, convection, radiation, just listing any 2 of them was 4 marks. And that's often a very sort of trivial question that people skip across and sometimes even leave out because it requires so little writing. Okay, I want to leave the heat there. I want to do a very quick overview of the particle physics. This is often material that is left to the end, just because it sort of naturally comes after you've done modern physics, and a lot of teachers like to do electricity before they look at modern physics, so that pushes the particle physics right to the end of the list. But the problem can be then that students think, well, look, you know, I've got enough questions. I'm just going to draw a line under this. I don't need this one. It's optional anyway, and just ignore it. And look, if you're desperately in trouble here, well, I'll come back to that in a few minutes. There can be an argument for doing that. But if you're looking at the top grades, you definitely should look at the whole course, but definitely here, because the particle physics is modern physics in general. There's a lot of questions on the paper for a relatively small amount of learning, but particle physics has like a question every year for, you know, what's, if you bring this down into notes, and the notes we'll send out this the next few days, it's about 3 pages and it covers everything here. So I'm not going to look at questions in this. We don't have time to do that, but just I'm going to run through the entire area of particle physics. And, you know, just to give you an overview of it, you'll probably find it a bit bewildering because of language if you haven't covered it already. But I promise you, if you start looking at Leaving Cert questions, by the time you've worked your way through 3 or 4 of them, they'll have begun to repeat. And the same material comes up over and over again because it has to, because there's not that much in it. So that is Ernest Walton, Ireland's first Nobel Prize winner in science. We've loads for literature. He was the first one in science. And he worked with Walton underneath the guidance of Rutherford, who carried out Rutherford's experiment, and came up with an experiment where they opened, like first time that they deliberately opened up the nucleus of an atom and split it into 2. So what they did was they fired protons at a lithium target over and over again. Most of the protons went through and didn't hit anything, but occasionally a proton would go right into a lithium target, lithium nucleus, and split it in 2 and fire out 2 alpha particles. Now, why is this so important? Why was it Nobel Prize winning work? Well, that's the reaction. Your proton, which is a hydrogen nucleus, goes into the lithium nucleus and it splits into 2 helium nuclei, which traveling fast are the alpha particles. But crucially, it's the plus energy that really mattered. Because not only was this the first particle accelerator, it also confirmed the equation E equals mc squared. So if you add up the mass of the 2 alpha particles, it is slightly less proton. So mass seemingly disappeared. But the energy of the alpha particles was much greater than the energy of the proton to begin with. So energy was seemingly appearing out of nothing. Mass was apparently disappearing, if that's a phrase you can use. And if you bung the energy that had appeared in for E, the mass that had disappeared in for M, multiplied by the speed of light squared, it matched perfectly. So this was the first experimental verification of Einstein's famous theory, equation that he had come up with, but had never proven to be true, that mass is in itself a form of energy. So for confirming E equals mc squared and for designing the first working particle accelerator, they they got their Nobel Prize. And they're still building modern accelerators built, like they're almost infinitely bigger than Cockcroft and Walton's, which was about 2 meters long. They're now working in places like CERN in Spain with the Large Hadron, which is a 27-kilometer tunnel where the same particles go over round and round and round in circle, gaining more energy in every circulation. And they're even in the news, or at least in physics news this morning, in that they came up with some interesting findings last night. I'll mention that again in a minute if I think of it when we get to it. So after Cockcroft and Walton, working towards like CERN and what's still happening now, many bigger, better, more powerful accelerators were built. And what they did with these was basically bang particles into each other at high speed. This is all about the search for the smallest particle. So how do you find what's inside an atom? You hit it hard and see if you can break it open to see what's inside. That's what Rutherford had tried to do. He found a nucleus. Now Cockcroft and Walton had discovered you could split the nucleus open. What about protons and neutrons and electrons? Can you hit 2 protons into each other and get something else inside? What's the smallest particle? This is what they were looking for. So they carried out loads of variations in these experiments over decades to see what might be there. But they kept on discovering particles that were slightly different, slightly bigger, slightly smaller, some with plus charge, some with minus charge, some with no charge. A number of names: muons, kaons, mesons. were all discovered, but they couldn't find any pattern in it. Sometimes you bang two protons into each other, you get muons. Sometimes you bang them in and you get kaons. What the hell is going on? What is inside those protons? Is it muons? Is it kaons? Is it mesons? What is in there? And they couldn't find any pattern to it all for decades. They came up with about 400 particles that seemed to be lurking inside protons and neutrons at different times. It became known as the particle zoo for the lack of order. Now, alongside all of this, there are three fundamental principles that must always be obeyed in subatomic reactions. You must have conservation of momentum, which is obeyed very strictly by subatomic particles, much more so than in the big world around us. It must have conservation of electric charge. Total electric charge before is equal to total electric charge afterwards, and conservation of energy. But we must now remember that energy includes mass. And when we looked at the beta decay of carbon-14, so carbon-14 is radioactive, it fires out beta particles. When it does that, the nucleus itself should bounce back. Like firing a bullet from a gun, the gun always recoils. But the carbon wasn't recoiling. The nucleus was sitting there by itself, quite happily not moving at all as the beta particle was fired out. And this seems to contravene both the principles of conservation of momentum and energy. So they came up with a theory that what must be happening is that there's another particle being fired out the back, which they named a neutrino. And they assumed it must be neutral because having an electric charge would make it easier to find. And it must be tiny, hence the eno from Italian. It must be absolutely tiny because they couldn't see any trace of it. And it took them 25 years of searching to see if these particles exist. And it now turns out that they do exist in great number. They're all over the place throughout the universe, but very, very hard to detect. They only very occasionally interact with other particles. So as well as all the stuff in the particle zoo, the muons, the kaons, the mesons, and so on, they now discovered neutrinos. It turns out there's three different types of neutrino. And then at one fell swoop, things got even worse. In trying to find the smallest particle, they kept coming up with more and more particles, not less, which is what they were hoping for. If you take Einstein's famous equation, which in one derivation is not E equals mc squared, it's E squared equals m squared c to the 4, get the square root of both sides, and you get E equals mc squared, but with a plus or minus. Now, the tendency in the early days was to ignore the minus. You know, what's a minus particle going to be? But as things got crazy throughout the 1950s and 1960s, people began to think, well, maybe those minus particles do exist. Went looking for them, and it turns out they do. So as well as electrons, we have the anti-electron, which is known as a positron. In what way is it a minus particle? Well, if plus and minus, plus 1 meets minus 1, you get 0. If an electron meets an anti-electron, you get 0. The particles eliminate, they annihilate each other. They disappear and their energy is transferred into 2 gamma rays. Same thing if a proton meets an antiproton, same thing. Neutron meets an antineutron, same thing. They annihilate, their mass disappears entirely, the energy is converted into gamma rays. You can also have the opposite, where a gamma ray loses its energy and briefly creates an electron and positron. But usually then the electron and positron meet up again and turn back into gamma rays. The maths of those, there's no new formula for this section at all. It's all E equals HF equals mc squared equals charge by voltage, all the stuff that we've learned in previous topics. So this is the overview. Late 1800s, people believed that atoms were the smallest particle. Everything was made up from atoms. Then we discovered the electron via the cathode ray tube inside the atom. Then the protons and neutrons with Rutherford's experiment. Then, over the following decades, throughout the 20s, 30s, 40s, 50s, all these other particles, and it amounted in the end to close to 1,000 other particles, all seemingly the smallest thing, or the building blocks, but with no pattern, until a guy called Murray Gell-Mann came up with the theory of quarks in the 1960s, where he said that all particles can be categorized as either leptons or hadrons. Leptons are fundamental, meaning there's nothing inside it. So there's nothing inside an electron. If you break open an electron, it disappears and its energy can convert it into gamma rays. Same thing with neutrinos. If you break open a hadron, you will discover they're all made from smaller particles still known as quarks. And they can be bunched together in bunches of 3 or 2, giving us baryons and bosons. Baryons and mesons. Now, if you haven't covered this material, I'm quite sure at this stage your head is spinning with the new language. But I promise you that that's the only thing that's difficult about this. The language is, I must have brought 10, 15 new words up in the last 10 minutes. If you've never heard them before, like in any language, loads of new words leaves you totally mystified. And like when we hear most languages, you think, oh my God, it's all so complicated. What are they saying? I could never follow this. But when you learn the words, you learn what they mean, it turns out it's all quite common sense. And it's the same thing here. So don't let that initial barrier of like all these words confuse you. They all make sense. How do you get used to it? By working through a few Leaving Cert questions. To make matters worse, there's not just one type of quark. There's 6 types of quark, each slightly different mass as well as charge. They're listed in you don't need to memorize these. And of course, every particle is an antiparticle. So if there's 6 quarks, there must be 6 antiquarks. But all like a proton is 2 ups and a down. A neutron is 2 downs and an up. All the particles you're more familiar with are made from some combination of up-down charge range, top-bottom quarks, or their antiquarks. And then finally, that's all particles fit into that map there. And they're affected only by the forces, and all forces originate from some combination of the gravitational, which we've learned about, the electromagnetic, which we've learned about, the weak nuclear, which we learn very little about. It's the one that pushes the beta particle out of the nucleus, and the strong nuclear force, which is what holds the nucleus together. In the nucleus of an atom, you have all those protons being pulled together all the time. Sorry, all those protons repelling each other all the time. So in uranium atom has 92 protons in its nucleus, every one of which is repelled by the other 91. So why doesn't it always break up? Why does it hold together at all? And that's because as well as that force pushing it all apart, there's also the strong nuclear force holding it all together. And that's the strongest of all forces, but it only operates over a tiny, tiny distance, the sort of distance you get in the nucleus of an atom. Now, that is everything in the particle physics. Like, I don't think I've skipped anything there. The details, of course, how does it come up in questions? Well, they might ask you the details of Cockcroft-Walton in an experiment. They might ask you to carry out calculations based on E equals mc squared, on E equals hf, and that takes practice. But it's not new information. It's just the same things over and over again. It's very easy to get disheartened doing E equals mc squared calculations because there's like 6 decimal places and it's so easy to go wrong. But like always, if you show the formula, show how you're subbing in, run through the steps on paper, if all you do is, mistake your decimal places at some point, it's usually only a 1 mark penalty. These questions are definitely worth preparing for if you're any way close to finishing the course. Right, so let's do a review of where we are before we finish up. So our course structure, the waves, light and sound mechanics, heat and temperature, electricity, modern physics, which usually includes the optional particle physics. If you're looking back through past papers, this is the way they're structured. But when you look at it, this year is going to be this variation on that. So 2 questions from 5 in section A and 4 questions from 9 in section B. Remember that this has a few odd effects if you've been preparing with the previous exam in mind. In section A, every question used to be worth 10%. You did 3 of them for 30%. Now section A is brought down to 26%. But it means that each question is worth more, 30. So nailing your 24 experiments, and that is a area where I would cut no corners. Walk into that exam with your full choice of 5 questions and pick the best 2 for you. And that's 26% by itself. And if you are properly prepared by just working through past questions, the questions that come up this year are going to be comparable to stuff that's come up in the past. That's been the case over and over again for the last 20 years. So if you prepare for that fully, there will be a reward. You mightn't get 26%, but even on a bad day, you're not going to go under 20. You're going to be up around 23, 24%. From, well, we'll talk about section B in a bit more detail in a minute. Remember here that 3 marks, it used to be 4 marks is 1%. For you guys, it's going to be 3 or 3.04, but basically 3 marks is 1%. In terms of timing, select your questions carefully. Give them plenty of time. I would say at the beginning, focus on your first 1 or 2 questions and then take a little bit of a breather, maybe after section A, and reread the questions in section B. Picking the right question is very important, and it's worth a few minutes of your time. And like I was saying yesterday when we were talking about that question on capacitance, don't, like, if you're intimidated by a question or then go, I don't like that stuff, don't write it off. It mightn't be your question 1, but it might be your question 4. Don't pick on comfort zone. Read through the question and quickly calculate, like, you know, okay, I know the definition, that's 12 marks. I know the demonstration experiment, that's 20 marks, you know, whatever they're telling you in the question. The maths, you know, there's a formula there. I can stick a formula down. I get 6 marks there. You know, give yourself a rough estimate of the mark you'd be confident of getting for each question and write it down beside the question as you read it. And then when you're finished reading the whole thing, go back and pick the 4 questions with the biggest numbers beside them, not the questions that you sort of like the look of. The weighting, we don't know. It varies year to year anyway. And this year will be a bit of an anomaly with the extra questions. But it's not going to, like, relatively speaking, the proportions will be similar to this. So the waves, light and sound, electricity tend to be the biggest sections. They're only slightly bigger than the mechanics and the modern physics. The heat and temperature is usually the least. Usually, I'd imagine 1 full question this year. Sometimes it's as little as half a question. Usually it's a full question. I'd say it'll be a full question at least this year. Remember from looking at the grade distributions over the years that this is a subject where if you are well prepared, you can do very well. And like that is going to be maintained this year. The percentages may vary. They might get a little bit more generous, but probably not as generous as last year would be my guess. But if you are well prepared, the H1s and H2s are there for the taking. If, on the other hand, you give up and just assume that things, you might get lucky on the day, that doesn't happen. They are prepared to fail people here or give them the very, very low grades. But anyone down here getting these grades has not gone in there having learned their definitions or demonstration experiments and their mandatory experiments. They alone will pull you up to these middle grades. The grade spread from the small number of people who did the exam last year. I just talked about this last week. I want to reiterate this point here, that a lot of people who signed up to that exam not having to do so, who already had a grade, went in there and still got a H8. Slightly smaller numbers got H6s and H7s. These are people who presumably had good reason to believe they could do better than the grade they got through the school system already. And they did. You know, I don't want to mock anyone's achievement, but I think most of us would regard a H8 as disappointing. My belief is that that's because they couldn't motivate themselves. Knowing they had a safety net, they let things slide in their study and preparation, and then they went in there at the end with no real hope of doing any better. And it didn't matter because they had their safety net. And that's fine as long as you're happy with the safety net. But most of you joining in for the last few days here presumably are going to do the physics exam. That means you're not totally confident about that safety net. And look, just bear this in mind, that human nature is that when you're not up against it, when you don't have a fear of total disaster, the motivation to study diminishes. But if you indulge that way of thinking, you could end up being down at the lower end of this table. Now we want to run 1 or 2 polls just to finish up our last bit of the discussion. Do you have the polls set up there, Fionn? First thing I suppose I'm just being nosy here. How many Leaving Cert exams will you sit?
Unfortunately, they didn't come through. I can quickly show.
Oh, did they not?
No, I can put them in there if you want. They shouldn't take long. You can, if you want to answer maybe a question while I do it.
Yeah, sure.
So just someone asked, do we need to learn off the quark composition of protons, neutrons, etc., or is there a logical way of figuring it out?
Both of those. So the quark composition of the proton and the neutron are the only two you're supposed to know. Let me just, do I have time? Got a minute here. I'll just go into whiteboard and explain how they work. I can get a working screen here quickly. So we have that quark, and this is listed in your table. So the up quark has a charge of +2/3, and the down quark has a charge of -1/3. So the two that you're supposed to know are the proton, and that's up, down. So how does that follow any logic? Well, the charge is +2/3, +2/3, and the down is -1/3, giving you, I hope, for 3/3. Yeah, which is the charge of +1.
I don't think they can see the whiteboard there. I'm not sure.
Did I come off screen share? I came off screen share to do that. Okay, so you've got the up and down quarks, and their charges are given in the table. So you have this information over here. The proton is up, up, down. So it's the charge of +2/3, +2/3, -1/3, giving you the proton of +1. Now, other combinations could give you a charge of +1, but they'd have different mass. Just while I have you on the screen there, the neutron is up, down, down, which is a +2/3, -1/3, -1/3. So that altogether comes to 0/3, which is the charges, and that's why the neutron has a charge of 0. So they're the only two you need to know. But if they ask you any other ones, and they have done, but they give you the information in the question that you need. So they'll tell you something like that it's made of charmed and strange quarks and they're anti-quarks. So how could you make this particle up? And it's just a case of messing around with the different combinations. It's 3 quarks or anti-quarks for a baryon. So anyway, you can put 3 of them together, or a meson is a quark with an anti-quark. And any combination that's possible will somehow exist in nature. So the rest of them are just logically, follow the information in the table, stick them together. And there's often different ways of coming up with similar particles. Definitely an example of where working through past papers will help you get used to it. Finn, did you get the first poll set up there, or either of those?
Yes, so just let me see. In physics, will you cover the whole course? I'm just going to write that down real quick.
Okay.
That's yes, no, is it?
Yeah, let's just go for a yes, no at this stage, yeah. And then I just got one more slide I want to run through. We might be like a minute or over.
Perfect. And there was actually just one more question. I'll launch the polls first.
Yeah.
There you go. I'm not sure if that's the way you were looking for the.
That's it. That's fine. It's better than the way I was looking at it. I was going to bunch them. So this, I'm sure, is interesting to some of you guys as it is to us, because we're only beginning to get information on this. Okay. That's interesting, because we're tight in time. We'll end it there, and there's one or two of you still thinking about it, and we'll share that. So I can see plenty of you are at least this stage thinking of taking, all of your subjects, which is, I think, the right thing to do. I mean, it's easy for me to say, but I can see why, depending on how many points you need, what course you're looking for. Like, everyone should be tactical when it comes to the end. I love the purity of learning up to this time of the year, but now you definitely have to be tactical. For many people, I believe the best tactic is the more, but not everyone is going to be in the same situation. So depending on what you need, what you have, I can totally see why some of you are down around a 4, but I'm glad not many are less than that. And in physics, will you cover the whole course? Do you have that one ready to go, Fionn?
Yeah, the answer to that and all that was just below.
Oh, sugar.
Reshare if you want.
Oh yeah, sure. So yes, okay. So loads of good intentions out there. Look, I think that's great. I don't want to be judging anyone. I know some of you said no there, and look, you have to figure out the situation you're in now based on what's happened in your class, what's happened with you, how much work you've done in the past, and does it make sense to leave it? Well, let's just tie this in with the next slide. So regardless of what position you're in and whether you're looking for the top grades or the scraping through grades, you should concentrate on mandatory experiments, definitions, derivations, and demonstration experiments. They alone will get you like a H5 at best, even if you got nothing else. So combine those with a few marks for always trying a formula, for having a go at every question, and you should be able to pull, with that being the focus of your study, up to 60-something%. If you want more than that, and I hope you do, well, then that is like the other 40-something% comes from the hard work and loads of problem solving and loads of practice. What I would say, whatever way you study, take one topic at a time. Don't jump around from mechanics to waves to electricity to modern physics. You might feel you're covering everything that way, but you're covering everything at a lesser level. Bury yourself in material for a few days. Just look at that one section of the course. If you need some variety, go and do your English or your Irish or whatever, but just in the physics, stick with one topic and let past papers guide your study. Pretty much at this stage, I wouldn't ever sit down again and just work your way through the book or work your way through the notes and think, I learn all this and then look at the Leaving Cert questions. The Leaving Cert questions you shouldn't see as a way of testing yourself. They'll come in June. The Leaving Cert questions are a way of organizing your study. So when you come across something in a question that you didn't know how to answer, that's when you go to the book or the notes and you check things out and maybe think, okay, I better study that a bit more. If it came up in the past, it might come up again. And then you move on to the next question. And it can be very slow at the beginning, but it will it'll pick up over a few days. You'll find yourself spending maybe an hour on a question at the beginning and 15-20 minutes at the end. In Leaving Cert questions, students who are doing very well often drop marks for material that they understand because they haven't drawn a diagram. And from their written text, there's some information missing that they wanted. And they would have been quite happy to give you the marks within the for the diagram. Whenever you come across any mathematical section, you do not give up on it until you've written down at least one formula and maybe 2 or 3 and made some attempt to sub it. And it is very unlikely you will not be getting marks, to at least some marks, if you do that. Give yourself time to select the right questions this year more than any. It's really important that you read all the questions and pick the ones that suit you best. I'm not going on about it again, but don't just pick on a vague feeling of comfort. Pick on how many marks you're confident you could score in that question. And then just to put out this question at the end there, should you do extra questions with time remaining? If everything is going right, if you have prepared right and you work your way through the exam and you're sort of, tactically on top of your game, the answer is no. You should not do extra questions. If your worst question, say, has got 40 marks, if you do another question and get 39, it's a total waste of time. You have to do better than your worst question for an extra question to have any value. And that's unusual, unless you picked the wrong questions to start with. So look, if you realize during the exam that you've messed up, then there can be an argument for fixing it by doing another question. But you would be much better off in your planning to really try to calm down and pick the right questions before you jump into it. If you have extra time at the end, you're much better off reading through the whole thing and looking, have you got a unit wrong? That's a mark. Have you left a tiny bit of a question out? Mark things off as you go along. If you skip something and mean to come back to it, have you remembered to do that? Pick up on those little things can easily add 3, 4, 5% to a grade. Doing an extra question very often, in fact, usually adds nothing to your grade. Okay, so I want to be. Is there any other questions there, Fionn? As I'm bringing you back in to say thank you very much for your support, and to Tracy and to Intel in general for the last week.